Ian is using the German concept of assistant professor, which means he assists the incompetent professor. Thank you for inviting me. It's been absolutely a super wonderful conference in every way, and I'm very glad to be here. I'm going to talk about cognitive hierarchy approach. So just to get us on it, most of you should know.
Do you have a microphone?
Yes.
Is it working?
It should be. Oh, it just goes to the video tape? Okay, so I'll speak up. Can I use both? Yeah, and then it won't interfere? Okay, let's do that. Yeah, okay, I'll try to work on this. Okay, so game theory is, as most of you know, a very general mathematical language which is used across social sciences and even in theoretical biology. And so games have players. They could be genes, actually, or representatives of nation states. They have information, issue strategies. Those lead to collective outcomes which are valued. Okay. And so there's several steps I'm going to go through. I'm going to talk mostly about cognitive hierarchy. I'll use that language in level K sort of generically, even though there's sort of small differences between particular specifications. Those are not, I think, of much interest today, although I'm happy to talk about them afterwards. I'm only going to show you a little bit of lab data, even though there's a lot of interesting lab experiments, some of which I probably aren't even familiar with. And I mostly want to pivot to look at field data applications. So this is an area in which, like some concepts in economics, like time preference and prospect theory, in which ideas that were completely originated in the lab with no real input from natural data, kind of were sharpened and honed parametrically, and then have been exported in a few cases to actually analyze lab data, including in areas of theoretical macroeconomics recently and things like that. So I understand this is an experimental economics audience, but if nothing else, you can go back to your colleagues and say, gee, lab experiments are really good for helping us build up models with a lot of careful detail and kind of try to get the details right and understand robustness, and then we can go understand why some movie companies don't let reviewers see the movie in time for consumers to know about it, which I'll talk about. And then finally, a fun example of an expert population playing a hide-and-seek game. So behavioral game theory, this is my old book from 2003, which I would love to have somebody update other than me, or maybe in collaboration. There was so much interesting new data in the last 15 years, lots. And in that book and in a lot of what I've done, I try to kind of organize things in three categories, which is something like initial conditions. There's a structural change, so you can think of what's going on as something like a new game, or there's new analysis that's needed, or you're playing once in the lab. What's a good model of that? Nash equilibrium is not going to be the best we can do. Although it may kind of work amazingly well under some conditions, it's not going to be the best we can do. So cognitive hierarchy and level K type models are designed to do that. Then we talk about learning. I'll just say a little bit about that in the middle. And equilibrium models in which mutual adjustment has taken place are useful too as sort of a target for where things may go in a medium or long run. And there are obviously familiar ones and quantum response equilibrium is the stochastic version that maintains the rational expectations piece, that people have accurate beliefs but allow there to be a stochastic response, which is often a very useful, captures a lot of behavioral regularity. Okay, this is just a reminder that I've done my homework. There are a number of other ways to think about procedural rationality. I think cursed equilibrium, I'll say one thing about, which is it's really designed only for blade information games, so it can never be a general theory. I think you know what I mean by that, right? Okay. Other theories could be. And quantum response equilibrium, I think, has been fascinating because the mathematical structure is quite elegant and interesting to work with, and it forces you to really think about what do we mean by noise and how does that get modeled. And so there's, if you like playing with kind of mathematical objects that have behavioral content, this is a fun one. And these are things other people have studied that almost all of these have some interesting intuition or in there. That's a reason why people have published papers and shown data sets. Okay, so I don't have time to cover those like I would in a course. I'm just going to focus on cognitive hierarchy. And here the idea is we're going to use in iterative steps of thinking. I think the earliest I think Ken Binmore told me that Luce and Rafa, in their amazing book in the 1950s, had a discussion like this, but I went and reread the book, probably not as thoroughly as I should have, and didn't see anything that looked familiar. But Ken in the 1980s talked about this type of model. He just didn't really develop it. And so the idea is to think about a hierarchy in a sense of almost like a computerized loop of thinking. The bottom of the hierarchy are level 0 naive players who aren't thinking about the game very much. It may be that they're lazy, they're cognitively overwhelmed, they don't care, they have some Pavlovian or highly adaptive response from there's a bunch of reasons that are lumped into this level 0. And I think they're interesting psychologically, but not very interesting in other respects. Level 1s think everyone is level 0. Level 2s think everyone's either 0 and 1 or just level 1. That's level K. 0 and 1 is cognitive hierarchy. And then you specify this in a particular way. And so in order to fill out the model, you need to say something about what the level distribution is. And do we think that's sort of universally constant, or is it a function of working memory, and does it change? So these are all, there are things you can ask about it. And what do the players at the different steps do? I told you the answer to that level K players best respond to either a mixture, a normalized accurate mixture of the lower level players, that's called cognitive hierarchy, or just the players below them. Okay. So let me step back and remind you again. This is something I think you people think about, but in the kind of dialogue with theorists who are often not as enamored of the approaches that we sometimes take, what a good theory should do is a whole bunch of different things. It should be quite general across games. I do not want to have a list of 100 games on 100 theories, or even 7 theories. Right? I mean, it might be that there's, say, 3, that they're fun. There's not a single unified theory, that there's 3. But we'd like to have dimension reduction on a general theory that was kind of developed to maybe explain one thing, like a 2/3 of the average game, and turns out to help us understand macroeconomics, say, or quality disclosure. I'd like the theories to be precise in the sense that maybe up to a parameter value, it produces a particular prediction. Not anything can happen. I think it's helpful if it's parameterized, but there are other approaches like non-parametric, because I think of the parameter values being able to capture heterogeneity and maybe skill and cognitive input and brain activity, things like that. And I would prefer, if I could insist, I would, but I can't. I would prefer that the good theories can account for not just choices, but data on visual attention, what people look at, or what they're thinking, if you can measure that. And even things like neural activity. And I understand that many economists, I don't care, don't raise your hand, I don't want to know. Many economists think there's a natural division of labor in which those data are not economic data. And I don't think that makes any sense. And also economics changes the types of data that people find useful. 20 years ago, nobody in economics studied subjective well-being, nobody. You would just be laughed out of the room. And now it's an exciting topic. And it's not because like somebody invented a machine to look into your brain and measure subjective well-being better than we did 20 years ago. It just became, people decided as a profession there was interesting data that we might be able to study. So I think we can decide as a profession whether these are data that help us, hone theories, so the theories have to explain choice and mechanism, or we can say, no, we don't care if the mechanism is all wrong if the choices are right. Okay. What is this distribution f of k? So Vince Crawford and others and us in originally our kind of expansive view took a pretty non-parametric view. Like the most interesting level types are really 0s, 1s, and 2s, and sometimes 3s. So to a large extent, if you estimate 0s and 1s and 2s, which is only 2 degrees of freedom, you're going to get most of the interesting stuff you can do, and you might be able to do theory with that 2-parameter version. Okay. If you want a 1-parameter version, here's one that's on offer, which is if the ratio of the number of k-level players to the number of k-1 level players drops off proportionally with 1 over k, so as k gets bigger, this sort of graduation rate of people going from k-1 to k goes down, 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 right, which is something like a bottleneck or a convexity maybe in working memory, then this axiom uniquely implies a Poisson distribution. That's important, is this distribution is axiomatically founded. And the Poisson distribution has a bunch of nice properties. If you're at Caltech, it's great because it has E. It's like scientific, it uses E. It's got a fancy French name, Poisson. And it's characterized by just one parameter, which is the mean and the variance. And again, you might think if you'd like there to be two features, then that's a bug. But if you like parsimony, then that's handy. Okay, and so we can talk about, and you can see what the distributions look like for various values of tau, which are the numbers we tend to estimate in the lab and sometimes in the field, which is around 1 or 2. A tau of 1.5, for example, shown in red, has the mode is 1. Level 1 is the most common type, but there are a lot of level 2s. And as you can see, because of the mathematical structure, the combinatorics, it drops off very rapidly, which is intuitively seems sensible, right? That there's going to be some level 3s and 4s and not many level 5s and so forth, unless there's some very special practice or self-selection. Okay, so a good canonical example, first Roger Gilney suggested this and Rosemary Nagel learned about it. It's called the beauty contest game. People choose numbers 0 to 100. You win if you're close to some known multiple of the average. 2/3 is an interesting multiple, so we'll use that. The goal obviously is to be below the average number, but not too far below, knowing that everyone else wants to be below. And so, of course, in Nash equilibrium, everyone wants to be below everyone. That's going to lead you to a boundary of 0. 0 corresponds to kind of infinitely many steps of iterated reasoning. And so I should add, it's easy to reject the theory that predicts 0 when you have a distribution because it can only go in one direction. And we did some experiments also early on trying to really explore robustness quite a bit. So we generated some data sets in which instead of 2/3 of the average, your target number is a positive integer plus a fraction of the average, and there's an interior Nash equilibrium, like 42, right? So that if people are just guessing 50, they'll actually be pretty close to the Nash equilibrium. Okay, and so here's some early results from the lab. This is from our data from 1998 from Singapore engineering students. The data are in maroon, the colors of the University of Chicago, and I think one of the colors in the Colombian flag, correct? Red? Okay. Anyway, that's, the data are in maroon, and so there's a few people picking 0. They don't win, right? That's an important thing too. So the Nash equilibrium prediction here is bad advice, right? And not only is it a bad prediction of one-time play, a population full of people choosing 0 is not going to reproduce unless something else happens. Dale Stahl has an early paper discussing that. And then you see mostly people around 25 or 30 or 35. And you see some very high numbers, which are, these are Singaporeans, and in Chinese, 8 is a lucky number. So there were like a few people being 80 or 88, which were not so lucky. It's not a lucky in general. Okay. This is some data from Claudia Kayser. She sent me, she did this 10 years ago when she was working at IBM with some kind of professionals. So these are people without probably much game theory training, engineers. And the data look pretty much like Singapore, including some high numbers and a lot of numbers in the center. More level 0 types. So you do, when people have some training or some really sharp insight, they can get the answer. They understand 0 is the answer to the question, what's the Nash equilibrium? But they often know also that that's not going to help you win the game. Okay, this is about 3,000 data points from 3 newspaper contests. So these are kind of like lab and field in the sense that there's a lot of structure, but it's not college student convenience samples, it's journalism convenience samples, usually very high income, overeducated compared to the average populations. And the great thing is with this much data, the spikes are kind of smoothed away. The minor spikes are smoothed away and you just see the modes popping up like 33, 22, and then around 1. The average was 23. Okay, there's a beautiful paper by Giorgio Coricelli and Rosemary Nagel and PNAS and a few recent papers. They basically are able to type classify people into level 2 or level 1, and the level 2 people have distinct brain activity in dorsomedial prefrontal cortex, and the level 1s just don't. I mean, they have common brain area activity in visual cortex and things like that, but dorsomedial prefrontal is part of a well-established kind of theory of mind or mentalizing capacity. Okay. There will not be a quiz on this slide. These are actually pretty old, as you can see, some of these citations. I updated a few. The main takeaway is do not say what a referee said 4 years ago, rejecting my postdoc Joseph Wong's paper. Most of the evidence about these hierarchy level cases really only from beauty contest games. It's ridiculous. If you did a big survey, of which this is a casual version, and Vince Crawford's Journal of Economic Literature paper is a really careful, super careful version. There's dozens of different types of games, and that's the whole point, is that you'd like to see if this same basic mental structure can really do a lot of different things for you in coordination, hide and seek, and then things that are right at the core of interesting things in economics, auctions. You could apply these to political competition we've seen, and so forth. And then somebody just sent me this macroeconomics paper on central bank policy. It was like, if you have any insights on how to manage the economy, I said, like most of the earth, I have no insights on how to manage the economy, but some of the very smart people thinking about macro have been using these multiple level types as well. Unfortunately, I have to skip that. Okay, lab is over, now it's field, yes?
Are people consistently classified as being of a given type and cross views?
I would say the charitable view is if you estimate within a class of games of a similar structure, like we have some old data where people played 22 mixed strategy games, 2 or 3 strategies, 2-person games, you get, if you fit their level types on like the first half of the games and the second half, you get a correlation like 0.6, like intra-person stability. That's probably the highest you're going to get, basically. Dan Fragidakis and David Roja have a recent game in which they try to type classify also in quite a demanding way, and they get kind of like 40 or 50% very sharply classified, and then a bunch of people not very classified. If you look across games at different structures, the classification, kind of the intra-person cross-game stability goes down a lot. But I should add that psychometric, this is something not all economists know, psychometric stability is never that high. It's basically 0.6 is like the highest it's going to be. Like if you measure risk aversion in a few different ways, you'll get a 0.4 or 0.3 or maybe 0.5, or 0.2 or 3, which is human working memory and patience, or human working memory and IQ. So 0.2 or 3 is interesting. Don't cry. It's not, I mean, if you could pray it to be bigger, we know the Pope framing didn't work, so we have reason to be skeptical. And then other correlations are 0. So I'd be very happy with the kind of stability correlation of 0.4, 0.5 per 6. Okay. All right, into the, thanks for the question. I'm glad I had a chance to clarify on that. This is a paper with, I forgot to put the citation. It's in AEJ Microeconomics. Robert Ostling and Joseph Wong did all the heavy lifting, and Eileen Chiu helped us. Robert was from Sweden. He emailed after he'd been at Caltech for a few months and went back home and said, there's this lottery they actually play here. Every day, about 53,000 people fill out one of these forms. And each of these 6 things represents a different number choice. You can pick a number from 1 up to 99,999. That's as many as fits on this little form. And in this thing, you can pick 6 different numbers if you want. Each number you pay €1. And whoever has the lowest unique number, so we call it looping, for lowest unique positive integer, wins €10,000. And then there's some other prizes. Okay, so it's quite an interesting game. We were tired of the beauty contest. So we were looking for other games that had some interesting structure. And this is great because you have a well-structured lottery. It turns out, as you'll see in a minute, the game theory is formidable but not impossible. And you get a lot of data like for free, right? We didn't pay a penny for the data. And so we have 49 days of the lottery, and then they stopped after a while, and we can see what people actually pick. And when we first submitted this, one of the referees said, your experiment in Sweden really, I think you could do a more interesting experiment than the experiment that you did in Sweden. We didn't do an experiment in Sweden. The Swedish government ran a lottery. But they made this mistake because it looked so much like an experiment, because the rules were so clear, And it wasn't even like auctions, which are another interesting area people have studied that's fairly well structured, because often there you have to try to figure out what the values are and how people are bidding. So it's much more econometrically challenging. Too hard for me. So this was cool. Okay. And so the first challenge is, well, what's a benchmark, equilibrium prediction? And then what can we say about level K and other theories? So it turns out, unfortunately, different numbers of people play, fortunately, not 53,000 people play each time. So it's not like an experiment where you have a big stadium for 53,000 people, nobody comes in and out, and they play 10 trials. Different numbers of people just sign up. So it turns out if you try to solve For the Nash equilibrium, it's going to be a mixed equilibrium. With 53,000 people, a fixed number, it's too hard. It's computationally intractable. Every time I've talked about this and there's a computer science in the audience, they email me, usually at like 3 o'clock in the morning, saying, I've been thinking about your problem and I think I can code it up and like solve it. And I'll email you when I'm done. Like, still waiting, still waiting. There's a particular combinatoric reason why it becomes extremely difficult to actually compute, like chess and other games. Right, okay. But it turns out, if you have different numbers of bidders, and you're willing to assume the number of bidders is Poisson distributed, it's a total coincidence, there's 2 Poissons in one talk, then you can solve it thanks to Roger Meyerson, who wrote some amazing papers on Poisson games, in which the number of players is distributed. He was thinking of things like voting, where you're not sure how many people will vote. So we took Roger's idea, and Robert and Joseph did the heavy lifting, and they said, well, look, it turns out if you have a Poisson number of people playing this complicated game, that simplifies it in an amazing way, and you can actually solve for the distribution of the frequency of time people pick people pick 1, you can't pick 0. People pick 2, 3, 4, up to the highest number. And the equations that generate those frequencies, so P of k is the predicted mixed strategy equilibrium frequency of picking number k, all right? The frequencies P of k satisfy this system of equations. And so you just grind away, and that you can solve. That you can solve. Okay. And so this is 350,000 observations from the first week of the lottery. The Poisson-Nash equilibrium is here. So what it is, it's basically the most frequently chosen number should be 1, and then 2 is slightly less, and it's slightly. And so it's like a slight decline until it plunges down and changes shape at 5,513. Right? And that number just comes from the math. You just produce this, you grind this machine and it produces this graph. So one thing you learn is the people who designed this game made a mistake. They printed too much stuff on their cards because they didn't realize when they designed it, nobody had computed the equilibrium. And they didn't realize that theoretically, almost nobody should pick a number above 5,000. So 95% of the numbers should never be picked. But from the point of view of game theory, that's a pretty bold prediction. Here's this game, right? I mean, try to think back 10 minutes ago when you may not have heard this or thought about, and if I asked you, what do you think people will pick, you get all kinds of crazy predictions. And if I said, I have a theory with 0 free parameters, 0, and it predicts that 95% of those numbers will never be picked. That's an amazing theory. And that part of it turns out to be correct. Okay, so as you can see, this is all the numbers plotted, all the possible numbers plotted. Mostly people just pick it. There are some weird spikes at certain round numbers. They may be lucky numbers for Swedes. Again, they're not that lucky because they didn't win, but they're focal or something like that. Okay, if we take the bottom 10% and just blow that up so you can see in more detail, you can see what's going on. Again, this is the Poisson-Nash equilibrium. And what you see is there's too many high numbers, too many compared to essentially 0. So again, they can only go in one direction. That's not too surprising. And there's way too many low numbers. This is the first week, right? So you get a lot of people sitting around Sweden thinking, I need to pick a low number that's unique. 1. No one's going to think of that, right? And so if you think about the psychology, you have to do 2 things. One is easy. You have to pick low. One is hard. You have to pick unique, right? And so they get the low part right, but not the unique part. And that's kind of the essence of these level K models. They're not thinking, is somebody else going to pick 1? And actually, you get a lot of 2s and 3s, and the 3s are like, I'm not going to be a dope and pick 1 like those other people. I'm picking 3. Who's going to think of 3? And there are like 97 other people. So it turns out when you have too many lows and somewhat too many highs, you have a gap from 2,500 to 5,000. That's where the winners are. That's where the winners are. Okay. So how does the cognitive hierarchy model do? So-so. I'm going to be very candid with you. The only version of the model that really fits pretty well is one that uses, rather than a logit stochastic response, it uses a power structure for some reason, and you need a stochastic response. Otherwise you're just going to predict people are going to pick 1, 2, 3, 4, 5, and you're going to get one of the features of the data correct, but you're going to miss that, thousands of numbers. So when you have a big number range like this, you need to have something that's going to spread out how people are choosing. And it turns out the best fit is if tau equals 1.80, which turns out to be pretty close to the lab type number. I mean, think of all the things that can go wrong between estimating these numbers in the lab and then some kind of field data. So the conjunction of this with the stochastic response function fits pretty well, because it basically fits the overchosen frequency of low numbers, and then as a result, it basically predicts that people are going to miss the 2,500 to 5,000, which is where the winners tend to be. Okay. All right, interlude. This is an important side point. Ernst Fair and I wrote a paper in Science 2006, and we wanted to lay out a little bit of a formula for when do we think, it's an idea that's been explored in behavioral economics, but it hasn't, in a way, gotten the attention it deserves, because it's really it's like the central question. Nudge schmudge, this is the central question. The question is, what are situations in which some agents acting in a limited irrational way will make other agents act in a limited rational way, like a kind of contagion or strategic complementarities? If you do it, I got to do it. Like you buy a whole bunch of Bitcoin, I don't know what it's worth, but I'm going to buy Bitcoin and make a bunch of money too. Okay? And that is not like a disclaimer, that is not an endorsement of actually purchasing Bitcoin. I will not reimburse you for your losses. Okay. But in other games, you have a strategic substitution, where if people are boundedly rational and are deviating from normative or equilibrium behavior in a particular way, the highly rational players, like level 1, 2s, and 3s, are going to fill in the gap. They're going to exploit the mistake makers. Okay. And so here's two examples. This is strategic complements. The Nash equilibrium is 0. If somebody else picks a number above 0, you should move above 0 too. So if they're irrational and you know the Nash equilibrium is 0, but you know you're playing level K type people, you'll move in that direction. So a small percentage of kind of irrationality or sort of naivete, let's call it, is going to make other people behave in a non-equilibrium way. Okay? This loopy game, on the other hand, is different. If a bunch of people are non-equilibrium by picking really low numbers, what you're going to do is you're going to fill in the gap and choose these high numbers, and you're going to help the aggregate population distribution look closer to equilibrium, close to equilibrium. So that's the formula for when does a little bit of irrationality make a difference or not. And it just depends upon whether it pays for you. You can get rich taking advantage of the irrationals, like in ARB, certain kinds of hedge fund ARB, or whether you can get rich temporarily riding a bubble or something like that. Okay. Actually, let me skip learning, even though I want to be sure to have time to carefully walk through these other examples. Okay, these are two actual movie posters for two. This was Neil Jordan's British-Irish movie, but was released in the US and internationally. This is I don't know how to even describe this. We can use it. This is a movie. And so what do you notice that's different than the two posters? There are a lot of differences, obviously. Color, and this is black and white. I just took out of a newspaper ad. This is, by the way, my middle name is Farrell, Colin Farrell Kammerer. So I was in Israel once, of all places, and a security guy looked at my ID. He was like, Colin Farrell, oh, like the movie actor. And then he looked at me and he was like, started laughing. I mean, it's just me. One thing you notice, well, I notice, maybe you do, is there's quotes from critics here. And the quotes are good, right? So somebody, I can't read very well, says, entrancing, a pure delight. Ondine is injected with a heavy dose of magic. A charmer, maybe one of the best films Neil Jordan has made. That's not that big of a compliment, right? Maybe he's only made 3 movies. That's like his mom, you know. An enchanting love story. There's quotes from critics. The reason is the movie, the way, this has changed quite a bit because of the internet, but in the old days, our data goes from 2001 to 2009. In those days, in the 2000s, the way movie promotion worked was you send screeners to the critics, or you invite them to a theater in Hollywood or New York, maybe like on Tuesday or Wednesday. The movie's going to be released on a Friday night, and they have enough time to see the movie and write the review, and they send it to you as a courtesy on Thursday to your publicity office so that they take a blurb from their review and they put it in the ad that runs in the newspaper on Friday. No such blurbs. The reason is they didn't even show it to the critics. Okay, so if you see a poster like this and there's no blurbs from the critics, is that good or bad? If you're naive, you say, oh, I don't know. If you're a strategic thinker, you think, probably they showed the weakest movies, or the strongest movies to the critics, and they did not show the weak movies like Killers to critics, because they're afraid the critics are gonna say mean things and they can't find anything to blurb. Another thing you can look at is, look for blurbs that are very short, like unusual, you know? Not like nothing you've ever seen before, you know. So these are things you can encode them as positive when you stop to think, could that really be part of a very negative review? And you go back and read the reviews, and often they're it's like some publicity person like manages to machine learn and find like this possibly positive phrase in this review that says how terrible it is. Okay, this is work with Alex Brown, Dan Lavallo. So in the period from 2000 to 2006, these are what are called big screen releases, 300 or more screens at the same time. So in fact, Ondine and other art movies don't even get into this sample. This is another one that was not shown to critics. We call that cold opened cold, meaning the critics didn't see it, with Eddie Murphy. And so in the old days, only 7% did that. And then it kind of went up, I think for various reasons. I'm happy to talk about this, but it's not cognitive hierarchy-ish. For some reason, this number drifted up over time. Okay, now why is this important? Because in the 80s, some famous economists laid out a very simple unraveling argument. And the argument was, if there's products that have kind of like one dimension of quality, now movies don't really fit, but there is a dimension called critic and fan ratings, and those tend to be more highly correlated than you might think, like 0.8, right? So even though it's not really one, their model works for one dimension of quality. And the idea is, suppose the quality is like uniform from 0 to 100, and producers can choose whether to reveal the quality or to give it to an independent critic who's going to be somewhat truthful, right? Then the high quality movies will get revealed. And then if you don't get any information, it's like, I know it's 0 to 50, the conditional expectation is 25. That means the movies from 25 to 50 are not, they're like the best of the worst, but they're getting pooled in with all these other movies. So the people who have movies from 25 to 50 will say, hey, wait a minute, our movie's a 41. You know, I don't want you to mistake it for a 14, for like an Ashton Kutcher movie. But then if you reveal the 25s to the 50s and the 50s to 100s, then people from 0 to 25, the people with 22s are like, hey, our movie's a 22, it's not a 9. And so the theory is that you should have voluntary disclosure of quality if consumers are naive, so that when they make the correct conditional expectation inference, if you don't get any disclosure information, okay? Okay, so that's the benchmark theory. If moviegoers understand that no news is bad news, because they understand the strategic motives behind what the studios do, then they shouldn't be fooled. But so here's the distribution. This is from something called Metacritic that averages 30 or more critics. And it's nice and Gaussian because you're average, so the law of medium-sized numbers works. And blue is movies that were shown to critics, and red is movies that were not shown to critics. And you can see the really high-quality movies they show to critics. The medium ones, a few of them they don't show. Down here, like the 0s to 20s, I think Ashton Kutcher movie was a 21 or a 19, something like that. Half of them they did not show to critics. So the reds are movies that were not shown to critics. And the idea is, if you're a naive moviegoer and you don't see the movie, you just look at the distribution, you think, well, it's probably like a 50. I mean, you're wrong. If you're a sophisticated moviegoer, you know that red is not cold open, means probably really low, maybe medium low, and there's a chance it's okay. Okay. So what we're going to do, now we're going to do, this is far from the lab, right? We have this movie data, we have a model that's based on there's one dimension of quality. You know, again, the lab is great because you can kind of make sure everything's pretty much right. And here you just have to make a whole bunch of assumptions and try to test robustness. So what we're going to run is we're going to run a regression of box office gross as a function of a bunch of control variables, like how famous the stars are and how many, the advertising budget, and whether science fiction might earn more money than like documentaries, and just pile everything you can think of in there. And then a fraction of the expected quality. And for movies that are shown, we're going to use the actual quality from critics as a proxy for expected quality. And for movies that are cold opened, we're going to plug in an expectation from the cognitive hierarchy model. Okay? So then what we're going to do is we're going to run a regression in which there's a cold open coefficient, dummy variable, and then the actual quality. But the expected quality, so we think this is the actual data generating function. But for cold open movies, the expected quality is above the actual quality because they're naively thinking it's probably better than it really is. Right? They think it's a 50, it's probably a 22. And so if we get a positive coefficient, that indicates naivete among the moviegoers. Okay? And by the way, I'm not really a great applied micro person. Unfortunately, my colleagues were, and we got a lot of really good advice. But when you do this kind of work, it's a real leap from a little specification in the lab to this kind of messy stuff. And you just hope that you get something like the sign is correct. And that you also hope if you can, you may be able to collect more data. Unfortunately, we're a little bit constrained, but the review process took so long that by the time we were making progress, there was like 4 more years of data we could collect. And so that actually turned out to be not helpful, a painful positive byproduct of having a slow-moving editorial process. Okay, so the regression I'm just going to show you is very simple. Is this number positive or not? That's it. Okay, so what I'm actually going to show you is a graph in which we run just this partial regression. We suppress these variables. And then we have residuals, and I'm going to plot the residuals as a function of cold and quality. Okay, so if the residuals are higher, they're positive for the cold open movies, that's evidence for a naivete. Okay, so this is the Metacritic rating of quality. This is the residuals. The cold opens are the reds. First, you can see the cold opens tend to be clustered on the left, where the low Metacritic ratings are. That's basically like the scatter plot I showed you before. The bar chart. This is the scatter plot version of that bar chart. And you can see there's a positive correlation. So if you think, oh, critic ratings have nothing to do with box office, there's a pretty strong correlation, but a lot of scatter. And you can see the red regression line is above the blue, and that gap is the cold open dummy variable coefficient. It's about 15%. So by withholding these crummy movies, they're earning about 15% more per box office weekend. And then we do a whole bunch of control variables. And as I mentioned before, one thing that's interesting is around this time, there's a big jump in how many movies are not shown to critics. It starts around 5 or 10%, and that's about 25. And again, a lot of things are happening in internet. Star Wars trailers are leaking out, and there's memes and all kinds of things changing. Okay, final thing is experts. So we're interested in individual differences, partly type classification like you had asked about, and are these level types, are they correlated with activity in the brain, or are there gender differences, or there's some evidence, for example, that working memory, how many things you can keep in mind, is modestly correlated with these level types of thinking, which is what you would expect if it's really a mental mechanism of imagining what people will do and imagining what imagining people do about other people. That takes some mental capacity to store multiple items in memory and manipulate them and think. This is a paper Peter Bossart, Chris, and Rahul Buie, and the key person here, Chris did all the work with the animals, and the key person is Tetsuo Matsuzawa, who's an extremely famous primatologist, an incredibly interesting person. I'm very honored to be able to work with him. And Rahul's contribution was to analyze the data and to make this Photoshop. Good work, Rahul. Okay. We are not the most powerful beasts in the planet. We are in some respects, like nuclear war, Twitter, which unfortunately may be related, scientific progress, big buildings, engineering, and things like that. But for many biological activities, some animal is better than we are. For example, this is an NFL wide receiver who's famous for being very fast, racing an ostrich. I think 60 yards and the ostrich wins. Okay. So Matsuzawa has an idea he calls the cognitive trade-off hypothesis. And if you think about evolution in the brain, This makes a lot of sense, although the details of exactly how it works, really is a deeply empirical question. So his idea is that as the human brain is basically a mammalian, as a primate brain, we separated from chimpanzees in the family tree 5 million years ago, and in that 5 million years, we basically grew this kind of thinking cap of neocortex. And we have a higher capacity for language, mentalizing is in the thinking cap, abstract reasoning, the ability to plan ahead. There's a whole bunch of things that humans, sharing with non-kin, non-biological kin, there are things that are kind of unique to humans that are all activities in neocortex. But the rest of the brain is still there, right? It's like you're taking a propeller airplane and you put jet engines in and the propellers are still there. So Matsuzawa's idea was, as human 2 and 3-year-olds start to spend a lot of time playing with other kids and being very pro-social and using language. They start sitting, talking, playing with other kids and their stupid devices. Meanwhile, the chimpanzees are playing hide and seek and learning how to play hide and seek games for one another, right? Because a lot of their life is much more competitive and not that cooperative compared to humans. And so it's possible that chimps are actually better at even certain cognitive tasks than we might be. If those are things that are ecologically very important for them, and which we kind of drop the ball, and a lot of neocortex and cortical and subcortical relations got devoted to higher order important stuff like talk, language, gossip, friend and foe, etc. And indeed, there are quite a few things people are not very good at that chimps are either about as good at or in some studies a little bit better, like upside down face perception. So for humans, if I show you a cup or a glass, a bottle, if I show you this, and I show you this upside down, I hope it's nicely sealed, you can recognize it as a bottle equally quickly, upside down and the same. But if I show you a face and I ask you who it is, it takes you quite a bit of time if it's upside down. I mean, you could do this at home. If I had more, I actually have some examples if I have more time. Chimps are pretty good. Like if you show them a familiar face, like another chimp that they should know in their group, they can recognize it upside down and right side up about equally quickly. So they're better than us at this weird skill, which is, if you're a chimpanzee, probably, had some special, either it could be learning or it could even be a selection for some kind of weird gene that's invariant to upside down face perception. We're not that good at that. Okay, and so one possibility is the chimpanzees in their natural ecology, and possibly a certain amount of genetic preparation and acculturation from their parents, are pretty good at competitive games. So here's a number. They play tag a lot, partly for status. So that one will hit one and they'll kind of run away. They play hide and seek. They have these things they call border patrol. Where the chimps have a border, and the high status chimps kind of go out and make sure the other chimps aren't peeking in. And then there's a last category, which I'm not going to explain, which humans have too. Anyway, so this is the family tree of hominids. There's orangutan, gorilla, pan-troglodyte. This is the official name for chimpanzee. This is Charles Darwin. We split off 5 million years ago. Interestingly, they are our closest kin genetically. We're really close together in terms of overall genetic makeup. And we're their closest kin too. So for example, horses and zebras are 1.5% apart in genes. They're not really quite that similar, even though they, as a surface, it looks like they'd be similar, except for, you could paint a horse this way, and they'd kind of look like a zebra, and you'd fool people. Meanwhile, we're only about 1.2% difference in genes between chimps and a randomly chosen by the American people to be president human, and orangutan is about 3.6% away. Okay, and in fact, interesting. Oh no. I really hope I don't get stuck on this. No. Do you have any idea how to get further in this? Here we go. Okay, good. Okay, I'm going to finish pretty rapidly because I'm just going to show you a couple of short videos, and then the data we collected from actual chimpanzees is very easy to present. So part of Matsuzawa's hypothesis about cognitive trade-off is that in the chimpanzee's world, keeping track of where things are, where there's a modest number of things, is a pretty big deal. Like fruit that falls from a tree, where the other chimps are in a fight. And by the way, these chimps are like amazing fighters. So when you watch them fight, I've never seen it, but Chris told me, they're like some kung fu movie that's like sped up, like, and they're really strong and vicious. So there are things that they can do that are just kind of superhuman in the sense of, they're much better than us. And we're not talking about, forget gorillas, right? They're like species of their own. The chimps are really terrific. So this is what's called a spatial number memory hold task. Spatial means numbers are shown on a screen, then they're quickly followed by a blank. So it shows where the number was, but it like covers up the number. They're only shown for 200 milliseconds. You're going to see it's quick. And then what the person has to do is to remember which number was where and press them in the ascending order from low to high. So you have to remember it was like 1, 3, 2, 5, 6. And 200 milliseconds is very tough. So if you trained in this and did a few hundred trials, you could get maybe 60% right. So we'll see how this person does. It means good. It means she got that right. It means wrong. So that's wrong. Okay, so that's a typical person with quite a bit of training, like maybe a few hundred trials. It's hard, right? It's hard. Here's our hero. He looks away. All right, so, and by the way, what they get paid, Apple, they get paid a food reward. And so they're eating after each trial. And Matsuzawa has one film of, they've done a lot of these experiments of a chimpanzee, I think he hears a noise like you heard there, another chimpanzee's making noise and he's distracted for 500 milliseconds. And in the video, the chimp looks away for 10 seconds. It's almost like showing off like, well, you want to see how long I can keep it in this my memory? Long enough? Okay, a couple more seconds. And then comes back. And it's 10 seconds of memory hold. I mean, that's pretty impressive. Okay, important caveat. These chimps are heavily trained. So this type of chimp probably has done this maybe 10,000 trials. And so, we know learning curves have a very regularized shape and they keep going down. They go down at a decelerating rate, but they do continue to go down. And also the younger chimps are better than the older chimps, much like in humans, in terms of basic things like memory, perception, auditory. And a lot of people have said, well, a lot of people in audiences I've talked to have said, sticking up for their species, have said, well, this is really unfair for the humans, and so there's an open question, which is, if you trained humans for 10,000 trials, how good would they be? And what Matsuzawa has said is, I've never been able to really get anybody to do it for that long. And he did say he had, the hierarchical Japanese system, he had 2 grad students and he told them they had to do this all summer, every day. That was, and so, it was only 2. And he said, by the end they were pretty good, but he thinks that there's something basic that the chimps are still just better at this than humans could ever be, controlling for training. But there's not as much data. We don't really have a rock hard answer. And also they have data from, that's 200 milliseconds of exposure, they have data from 90 milliseconds, which is kind of barely above the perceptual threshold. And the trained chimps can do it, can get maybe half right. They look like the human you saw, and people are like hopeless. So again, we don't really know if it's a true additional skill or not, but it's pretty impressive. Okay. All right, and so what we did in this last study was to play matching pennies games. And so these are payoffs. And what we're going to do is we're going to vary x. So a lot of you will know, if you know some game theory, you can figure out exactly what might be interesting here, which is in this game, it has a very unusual property, which is that there's a unique mixed equilibrium. The row player gets these bold black playoffs, and the column player, the red left and right payoffs. And so it's similar to a hide and seek or a competitive game. You know, one player gets a reward and the other player gets zero, whatever cell they're in. And so you expect to see a mixture. And more interestingly, as we vary x, it doesn't vary the predicted mixture probabilities of left and right at all. So the player whose reward is being varied, we're going to vary x from like 2 to 3 to 4, shouldn't change at all in equilibrium. Like, what kind of theory is that? That's the same theory that did pretty well in loopy. But the variance in the row player's reward should affect, through this adjustment equilibrium process, it should affect what the column player does. And specifically, if x is 4, for example, then the column player should play right a lot more often. And that's why the row player should be satisfied to play 50-50, because they're not going to get the 4. It's almost like a big number, the players are going to adjust so that if I think you're going for 4 all the time, I'm going to win by going right, and I'm going to go right so often that you don't want to go for 4. And so these are equilibrium mixtures. So what we're going to do is we're going to play these matching penny games with chimps and humans, varying x over a couple of different numbers and seeing if the equilibrium mixtures move in the right direction. Okay. And so in order to do this, Japan is an incredible place to study primates. So the Nagoya Primate Research Institute has 50-some primates, I think 15 chimps, I think like 9 gorillas and a bunch of orangutans, and they have a Japanese macaque. Partly the Japanese are very monkey crazy because they have their own, there's a macaque that's native to Japan. And some of you, if you've been to Japan, you may have been up to these, in the mountains, the macaques, like there's a macaque park where you can like play with the macaques, all these beautiful pictures of them with snow on their hair, and it's really wonderful. Anyway, if you go to the PRI in Nagoya, they have a big outside play area that's meant to kind of simulate the jungle in an industrial way. So there's, just like in most zoos, there's a tire and a rope they swing and play on, and the climbing structures. And then they have this underground testing facility, and they come in, and Chris trained these 2 chimpanzees to play on dual touchscreens to play a game at the same time with each other. Okay, so the way it works is in the matching pennies, left and right and top and bottom is going to be just left and right on a touchscreen. So they're going to see these 2 rectangles, and they're going to each touch around this at the same time. Okay, and one player has the payoff structure that if they match, like if they both play press left or they both press right, then they get a food reward, and the other player does not. And the other player wants to mismatch. And they play this in chunks of like 500 trials. They're very quick. And there's a bunch of other interesting things about animal work. This is a really outstanding animal research place, and so they did everything right, as far as I could tell. The other thing that's notable, it's not ideal compared to human experiments, but the chimps are very status conscious and they kind of fight a lot. So these are all mother-child pairs. So it's a mother and I think 2 daughters and 1 male son. Okay. All right. So it's not a random, you can't just take randomly assigned chimps and put them in there because if there's a status relation, they'll fight because that's a big part of their lives. Okay. And the other thing, again, you can see from the picture is they're actually in the same. One of the challenges with animal research is if one animal is like in one spot in the building and the other animal's in another spot, how do you know that they know they're playing another animal? And so they're making a lot of progress in this. Chris now works as a postdoc at the Indianapolis Zoo, and they have trained about 8 orangutans on these touch screens. It turns out, just like your children, these animals train on the touch screens very quickly. I mean, they're really used to pressing stuff, grabbing stuff and getting a food reward. The difference is that they press and the food reward comes out of this little slot. But they quickly learn, oh, this is pretty much the same, is even better. So they've done some really incredible stuff. They use Skype, actually. So what they did is, to train the chimps that there's other chimps, is that they actually have them, they recruit them and put them in different places. So they kind of know the other chimp is somewhere, but they can't see them. And then they go on Skype. And just like with my dad, who was 80 when he first used Skype. It's like, how does this thing work? Are they really there? Is it a time lapse? My dad was exactly like the chimpanzees, basically. And so we're very hopeful that we can study cross-species collaborations and things, exploiting the fact that these animals, especially the chimps, are, they can learn basic reinforcement and concepts of that another animal might be on a TV playing with them and things like that. We think so. Okay. Anyway, and so as I said, this is the basic payoff matrix. We're going to change, in some games, x and y are going to be 2. In another game, x is going to be 3 and y is 1. And another game is 4 and 1. And so that's going to vary. The matcher probabilities, left and right, is going to be 50% all the time. So we're going to change the food the matcher gets, but it should not change behavior. Again, this is a very bold, kind of ridiculous prediction. And the non-equilibrium, it's ridiculous, but we'll see what happens. But the changes in the matcher's food should change what the mismatcher's probability of right is. And as we move across these x and y values, they should start to play right, not 50% of the time, but 75% and 80%. Okay. And again, I misspoke, I said 500. They play 200 trials each day for like 10 or 20 days in a row. So we have a long time series for these different animals. And so this is symmetric matching pennies. So each of these, a color is a pair of animals playing in a partner protocol. So this is Ai. Ai is actually quite famous in Japan. She's on TV all the time. It's an Ayumu. So if you plot the percentage, this is the mismatcher probability frequency of playing right out of 200 times. So they played right 120 times, it's 60%. And this is matcher playing right. And they alternate roles also. So for each subject, you have a mismatcher right percentage and a matcher right percentage for each person. And you have these long strings of data. And so here's Ai and Ayumu in red. Another pair is Chloe and Ku, they're over here. And here's Pan and Pal. And this is the Nash equilibrium. And this is standard error bars, basically. So the standard error bars are not, they're not put on these icons, but they're that size. They're very precisely estimated. So each of these is really significantly different than 50-50, for sure. They're not really nailing this. But if you can see, if you average them, it's very close. If you average, they're very close. And the other thing is, there are sequences, we spent a lot of time in the paper, it's in Science Reports, doing what are very typical tests with randomization with humans, which there's a large, like, do they exhibit negative autocorrelation? Is it like a gambler's fallacy? I play left, and then it's due for a right. Do they have long enough runs? And mostly they look kind of random. There's times when the animals don't seem motivated, and they'll pick left. They'll just pick left like 27 times in a row. So, we don't know what's going on. So about 10% of the data are pretty messy. They're data you would not see in humans typically. Typically long streaks, like you're just asleep at the wheel. But even including those data, you get close to reasonable randomization, and you get patterns that look kind of like human data. Okay, asymmetric matching pennies. Here we've moved the Nash equilibrium up here. So remember, we've changed the payoffs to the matcher, but they should still be picking 50-50. And the mismatcher should now move up and be choosing 75% of the time. And what you can see is, this is a cognitive hierarchy prediction. Quantum response equilibrium is really, somebody mentioned that the other day, thank you, is very easy to see here. It's basically just going to be an arc from 50-50 randomization, because that's where the quantum response parameter is pure noise. It's going to be a continuous arc tracing from 50-50 to Nash, and it's here. And so quantum response kind of does okay. But a bunch of you can see, the prediction that changing the matcher's payoffs will not change 50-50 is not right. They pick right, they pick left more often. So they go to where the high payoffs is. And again, this is all the data. So if you look at the last part of the data compared to the beginning to look at learning, there is a little bit of learning toward Nash. And this is the third game, which is we've changed the payoff just slightly again, and we moved the Nash equilibrium up a little higher. And now you can see the data is a little more sprinkled around. Cognitive hierarchy does not do great on these data, to be honest. It may be because it's really kind of a model of initial conditions, not extremely long-run learning. Okay, and ready? This is the big picture. Okay, so, sorry, two big pictures. We also have some human data. So this is the inspection game. That's the one where the highest reward is 4 units of food. And you can see the chimps are here. They're all kind of clustered around the Nash equilibrium, a little bit off here, a little bit off here. If you take the average of the chimps, they're really, really, really close. There's 2 human samples. One is Japanese people who came to the lab, and they did the same task. In fact, we basically, there's a trend in animal-human research to treat the humans like animals. First of all, we are, unless you're a creationist. And what that means is that in the animal protocols, we don't read instructions and have quizzes, and thank God they don't look at Z tree, right? Even the chimpanzees will be like, what's wrong with these, what's up with these fonts, humans? You know? Anyway, so we don't read them instructions. We basically put them in front of the screen, and they press, and occasionally they get a reward. And so they have to learn the entire structure by trial and error. You know, we don't show them that graph, right? And so the humans, we do the same thing. We said, you're going to play a game in which you press left to right each time. You can do whatever you want, and sometimes you'll get a coin, and you can keep your coins at the end.
Did they know? But if they were at least informed that they were not playing against the computer, or not?
Yeah. So they know there's another person. And it was just like with the chimps. The chimps come into this little, like, kiosk, and they see there's another chimp pressing at the same time as they are. And we hope that they draw the inference from the synchrony of the choices that this other chimp's press affected whether they got money or not. I mean, we can't, you can have a quiz and try to debrief from the, not very helpful. I think the observers of the primates are pretty convinced that they have a concept they're playing another animal. I mean, first of all, there are a lot of things in natural ecology where they're playing another animal. So it's not the strangest thing. It's not like you've taken these asocial creatures and put them together. And you can see they look over at one another. Sometimes if one of the chimps is taking too long, they kind of look over like, hurry up. Okay, so here's some human data. And then we added some other data. Matsuzawa's group also has access to chimpanzees in the wild, semi-wild, at a nature reserve in Busu, West Guinea, Africa. And in the nature preserve, there's a bunch of Africans who work there as handlers. And so they played these matching penny games with them, although the protocol was different. They didn't use touchscreens. They basically just had bottle caps, and they did it kind of by hand and said, just either your bottle cap's gonna be up or down. And then when he wants to match, and they had a little cubicle. And the great thing was, we were able to pay them a lot of money because their country is very poor, very poor. So it's kind of hard to figure out what the purchasing power of the money we paid them is, because it's a very small-scale society, a very underdeveloped society. And but I think our computation was something like $150 an hour. So the Japanese were paid a small amount, and the Africans in purchasing power, in equivalent purchasing power, were paid a huge amount of money. And you can see they basically just are around 50-50. They don't seem to be moving in the Nash direction. Okay, so finally, my claim is this is the best evidence of Nash mixing ever. This should be, if you write a game theory textbook and you don't put this in, I'm gonna be mad. I'll be mad at you. Because if you look across the 3 games, I put the structure here so you could be reminded, across the 3 games, there's 3 different Nash equilibria. And then what I've plotted is just the average across the 6 chimps, right? And in this game, you could barely tell which is the prediction, which is the data. Right here, you can see there's a little bit of a miss. And here, there's really one miss out of the 2 different roles, matcher, mismatcher, and 3 games. There's really one role game combination where they're really off, which is here, where, remember, we've changed the payoff so the matcher gets more, from choosing left, and they actually do choose right less often, i.e. left more often. So they're kind of overreacting compared to the Nash equilibrium. But other than that, they're really, really close together. Okay. And by the way, this is a graph from my paper. If you look back at about 10 or 15 or 20 experiments with human mixing, usually much smaller strings of experience, like 500 trials is typical, or 250 trials, and you plot the actual frequency relative to the Nash mixture. First of all, the human data is pretty good in general. The correlation here is like 0.9. So the idea that humans don't mix like the models predict, I think is just a myth, if you look at this picture. It's true it's not 100%, and there are some big misses. I mean, there are cases where the Nash mixture predicts something and the data is way off. And here's our data, Japanese and Japanese humans and the Africans. And so it's not the case that our humans were, less good at mixing than other humans who've been studied. Okay. And we're actually kind of proud of the fact that we have, these are not college students at Caltech for sure, right? These are Japanese people visiting PRI who are mostly older. Some of them are journalists or other scientists or, spouses who came to visit there. And then the West Africans are probably 25 to 30, 40-year-old men living in, they're better educated than average probably in West Guinea because they work in these reserve, but they're being paid a tremendous amount of money. And their data are not dramatically different than other data. Okay. I'll just say a couple things. Why are the chimps closer to equilibrium? So we estimate some learning models like fictitious play, and it turns out that the learning rate is higher for the chimps. They seem to be kind of paying attention a little more carefully. Again, that may be part of a cognitive trade-off, that this game is somehow interesting to them or familiar. The other thing is the chimps are faster than humans. So if you think about earnings per minute, I mean, they're really racking up the pay. And interestingly, the matchers are faster than the mismatchers. And we can't think of any sensible reason why that would be, except matching what another person did is like imitation. And imitation is a major driver of animal learning, particularly humans, but for primates as well. So the idea that if mommy reaches over there and I reach over there, that ends up being either sort of an innate reflex or something that's getting reinforced. Somebody mentioned mirror neurons, and the neurons that are dedicated to kind of replaying in our brain are doing the same thing as another person did. And this is just a kind of fun fact. I don't know, if somebody has a theory that predicts behavior in games and choice speed, it can explain this. That would be a pretty impressive theory, right? I mean, it's not what game theory is designed to do, but it is an interesting observation we made. Okay, so the conclusion from this, and then I'll draw some general conclusions. So in these data, the chimps are closer to Nash equilibrium than two different human populations. We don't think it's incentives. Again, we haven't really sharply nailed down the cognitive trade-off idea. It's kind of like a lot of things in biology. It's not really a mathematical proof. It's sort of a theme that, for which various data seem to match. I mean, if theorists came along and had more to say about this, it would be really exciting. We think part of it is they're more responsive to the opponents and the path structure. And here's a quote from Ken Binmore from quite a while, 30 years ago. And he says, we could think about game theory as evolutive. It's not how smart people are, or do they take a course at a business school, but the players in evolutive game theory need not be thinking creatures. They learn by trial and error adjustment, and that kept moving the ecology of which they're a part. And so the idea that this is something like a lifelike, it's an abstract version of a game that chimps have a lot of practice with. That's a part of their life and death repertoire. Okay, so let me just remind you about the paper with Fair, which is game theory in the sense of equilibrium prediction actually does surprisingly well in a couple of cases. So one is, I just showed you chimpanzees playing an abstract game under long periods of time. So including the beginning, where they may be out of equilibrium, and then the end, where they may have learned, and they're really close. They're really close. And that's in a game where the main prediction is that if you change what the food one player gets, they don't change their behavior the other player does, which is sort of really the hallmark of either strategic thinking or adjustment. I mean, that's amazing. And the formula is, if one player is out of equilibrium, I'm going to respond in a way that will tend to generate cycles that pull them into equilibrium. And a key thing there is evolutionary advantage of practice. Another thing I didn't have time to show you is in the loopy game, the lowest unique integer in Sweden, after 7 weeks, they're really close to the Poisson-Nash equilibrium. I mean, it's amazing, just by trial and adjustment. And look at the adjustment dynamics. It looks like what happens is there's actually a TV show on the news, and it says, you know, the winner was 2,715, Sven Northson, and then the next day, everyone who picked a 1 picks, you know, like 2,715. So in the data, it looks like there's a kind of sluggish imitation dynamics, where they kind of anchor on what they picked and they move some fraction of the way toward the winner. And that dynamics in this large population in 49 days of play is enough to kind of move them. So this amazing exotic national equilibrium is a good prediction of the 49th day of play in Sweden. It's a pretty good prediction, like the second or third week. Okay, so I've given you kind of a whirlwind tour of cognitive hierarchy and some other things. The cognitive hierarchy model does not help us particularly understand the chimps. There's a whole different story, we think, that has to do with the evolutionary basis of strategic thinking in other species that's very close to us. A reminder that this has been used in a lot of lab games. I only mentioned one, and I gave you a little bit of a list. Again, Vince Crawford's review on this is extremely meticulous. And also he ties each of the games to kind of a natural example, like from literature, from military history. So that's cool. I showed you some field data from a well-structured lottery, and then from movies, which are messier. I think these have been open questions for years. So if you tackle some of these, I think you'll have a little bit of a head start before other people jump in. One is, we would love to endogenize these levels of thinking somehow. You know, why is it? Is it some sort of hardwired trait or ability? I don't think so. Why is it that somebody would stop at 2 levels or 3? There's a beautiful paper of Alois and Penta from Pompeo Fabra about this. Maybe some new stuff. And then we'd also like to have a more unifying theory of level 0, because in different games, sometimes level 0 players randomly picking, like 0 to 100 is a good guess. But other times, like, it looks like they'll pick a focal strategy, or, you know, if you have a visual display, they may pick a certain area of a visual display based on salience and things like that we've been studying. So I think that salience may be a general principle, but we want to be as scientific as we can about what that means. I don't want to just pick something and say, see, isn't that salient? Oh, that's what the people, I don't want to have people's behavior tell me what's salient. I'd rather have a sort of predictive concept of salience. And there are some ideas from visual neuroscience about salience, but it's usually what's called bottom-up, which means if I show you a picture, what do you look at right away? That's kind of a solved problem. But a lot of what we think about as science and economics has to do with the content of messages, or some unusual event, or, you know, a weird number, or a national holiday in Colombia that coincides with the start of a conference, or just to pick or the Pope, you know, any salience theory has to have the Pope, right? You can help us with that, right? So I think someday it'd be nice. I don't want you to have to email me. It'd be nice to have a document that says, here, like, feed your game structure, including maybe visual and semantics, and we'll tell you what we think salient level 0s do, and then you can build the hierarchy up from there. And you hope we can explain a bunch of games pretty well with a general structure. And we're going to have some terrible misses where the theory's really wrong, and then just like when we have an earthquake in California, you know, we learn about how to build stronger buildings. You go back, you take the miss and go back and try to come up with better theory. Okay, thanks.